Good afternoon, everyone. Yes, so I'm Abhimanyu. Thank you, Sergey, for inviting me. I recently defended my PhD at the Delft University of Technology in the Department of Systems and Control. I worked on Max Plus discrete event systems. So discrete event systems that can be described using Max Plus algebra and associated idempotent semirings. And one of the topics I studied was stability analysis. So I'm from an engineering background, and a lot of things that I do has roots in applications. So what I start with is an application, and then I see how I can use the tools from Max Plus algebra to answer some decision questions and look at some decision problems. This is one of the chapters of my thesis. I'm still working on publishing this paper, but I would love to present this topic to you guys. So again, I work with applications, so it's a good idea for me to start with an example for such systems. So what we consider are man-made systems, and by man-made systems, I mean railway networks or manufacturing systems that can be represented using graphs, and their dynamics is derived from operation rules. And as an operator, the idea is to maintain boundedness of the system. So that is where stability comes into picture. But we would like that in case a disruption occurs, we are able to minimize the delays in the system and keep it running in an efficient manner. So, of course, a lot of things are based on intuition. Even the modeling aspect it is derived from human knowledge. There's no physics involved, let's say, and things can get complicated as the network becomes bigger, and we can actually have like combinatorial explosion of decisions that from which we would like to choose from. So okay, we start with a macroscopic model, right? So we start with a very basic model. We say that we associate a clock to each and every station, and the clock it notes the arrival and departure of trains. So here the arrival and departure are discrete events, and we look into time discrete event systems. So we look at the timing of these discrete event systems. So we have, let's say, trains going between these three stations, and the next step in modeling is to provide precedence conditions, so precedence constraints between these clocks, right? So let's say the train leaves from station 2 and arrives on station 1, then there should be a difference of these 44 time units between the two clock values for that particular cycle. And let's say we would like to look at boundedness of the system. So what would that mean physically? Well, we would not like the trains to accumulate at a particular platform, or we would not like the trains to accumulate between the stations. So that would translate as these clocks ticking at a synchronized rate, right? So if you have the clock at 2 ticking faster, that means trains at station 2 are leaving faster than they are actually arriving at 1, then you have a problem in the system. And that is where the boundedness notion comes in, and that is more or less what we study. So the idea is that stability can help us more than just deciding on boundedness of the system. So we'll come to that part later on, but just for the modeling aspect, this is where Max Plus algebra comes into picture. So we can represent these precedence constraints using Max Plus linear equations a lot of the times. Okay, so looking into stability. So because again, I'm more from the physics engineering side of study. So I thought about such systems from a point of view of physical systems and how stability is studied in those systems. So let's consider an example of a pendulum. Let's say the pendulum is at an equilibrium state and we flick it. So we inject energy into the system. What happens is that we throw away, we inject energy and it goes to a higher energy state somewhere. And because the system dissipates energy, so that is the idea of stability here, it will eventually decrease, the energy will eventually decrease and the system will come to an equilibrium that for this case is the lowest energy state. Okay, so this is all physics, and it is difficult to think intuitively of such a stability notion in a man-made system where there is no physics, there are no Lagrangians or Hamiltonians. But yeah, that is what we would like to see. That was my motivation. And coming to the stability of man-made systems, we would have, let's say, a railway network where the equilibrium state can be, for instance, the timetable that we design. And we would like to know if we have a certain amount of disruption in the system, does the system have the ability to dissipate that delay, that time delay somehow, and come back to an energy state that is minimum at the timetable. So the energy states can have, the levels can have a very different, let's say, schematic. And I chose this one because, yeah, it will come later. It looks like a max plus polyhedron. Okay, so this is all example. This is mainly motivation of my study. And from now on, I'll dig deeper into the mathematics of all of this. So to begin with, we define the system dynamics as a difference equation. Like I suggested, that this is where max plus algebra comes into play, and we have that x, the state, a vector that has the clock variables in it. So each state represents time, how it relates from one cycle k minus 1 to the next one, that is k. And here, for generality, I've also included a state L of k that is discrete. So I say that we can have multiple ways of operating the system. So this, for a fixed L, we say it is in a certain mode L. So it can be in mode 1 or 2. And yeah, so the notion of stability from application point of view is that we have bounded buffers. And what I mean by buffer here is that if we pick a certain time, so event step k, so event cycle, I would like that the states are bounded for that, so they are between a certain threshold. And you can imagine that this state x, because it represents time, it will keep on growing with the evolution of the system dynamics. So that is one of the ways. So I say that for a particular event cycle k, I have a bound on the state from above and below. And another notion of stability could be that the rate of growth, like I suggested for the railway example, it becomes constant, or you have, let's say, at an average, all the states growing at a certain certain synchronized quantity, so at a level that nothing blows up, let's say. Okay, so there are, of course, this is this is the slide why I'm here in this workshop. I use a lot of tools from max plus algebra to study such problems, and the simplest abstraction of any dynamical system is a linear system, and for us that would be a max plus linear system, right? So we would have that F is just a single matrix A, and we have a max plus linear system. So these systems are, so there are studies on for such systems are in abundance. It has been studied for decades, and we know everything about it. It's the mathematics is very elegant, and we can say a lot of things, especially about the equilibria, the convergence to those equilibrium points, and yeah, using tools from graph theory especially. So again, the fixed point here is the max plus eigenvalue problem. So we say that the eigenvectors V here, they satisfy this max plus eigenvalue problem, and if such max plus eigenvector exists, then system will have certain stability properties. And the sufficient condition for that is to have this matrix A irreducible. So again, there are certain properties that allow us to derive just from the existence of a max plus eigenvector these stability properties. So these are the properties, and they are very important. The first one is additive homogeneity. Yeah, so this is mainly a sort of linearity. So it's, you can have a scalar mu, and you can shift X, and you can get the dynamics back. And then we have monotonicity and non-expansiveness, and these two properties become equivalent under additive homogeneity. So you can have, if you have monotonicity with additive homogeneity, you have non-expansiveness and the other case as well. So again, these are mathematical properties. Of course, we like, as engineers, we like to find meaning in everything. So there is physical meaning associated to these properties as well, and that's why they are actually necessary for the case of the application, and they help us a lot in analyzing the system. So what I study is a bit more generalized case. So we do not now have a single matrix A, but let's say a set of them. So I assume that this set, this curly L is finite. So I have finitely many modes of operation, and I can choose from them using scheduling variables. So this is usually the case in application, but for now, I assume that this L of K is arbitrary. So again, this I call a switching max plus linear system, and the mode you can think of as production recipes in a manufacturing system, for instance. So for every L, you have a different production recipe. So the problem now is that a lot of properties that hold for max plus linear systems go away. So again, we have additive homogeneity, that is very nice, but because of this discrete variable L of K, we have a loss of monotonicity and a loss of, again, non-expansiveness, especially when we do not know in advance what this switching sequence will be. And like I said, these properties are very important for a lot of mathematical properties, a lot of mathematical theorems and that we derive for max plus linear systems. Okay. Again, I even generalize the class of systems I study further. So I say that it is any function f that satisfies three assumptions. So first of all, it is structurally finite. So I'm not looking at R and epsilon. I'm only looking at Rn because the state, the elements of the state represent time. So I would like to have that if the system starts at a finite time, the next state will again be a finite value, not epsilon. The second one is continuity, that is mainly for regularity purpose. And the last one is additive homogeneity. And yeah, so physically speaking, this means that if I if I have a printer, let's say, that I describe using max plus linear or switching max plus linear system, and I operate it today, it will, and it behaves in a certain way, and I operate it tomorrow after, let's say, mu amount of time, it will behave similarly. So it will only translate, the dynamics will just translate in time. So that is the idea of additive homogeneity. Okay, so for conventional systems, the notion of stability requires this assumption. So we assume that the dynamics is defined on a normed vector space. And we study stability using Lyapunov notions. So these notions are quite nice. They again generate from mechanical and engineering applications. So the idea is simple. We have, we have an equilibrium point x star with respect to which we study stability. And this equilibrium is an invariant property, right? So if I start at x star, I will remain at x star at all times. The stability property suggests that if I start at a particular distance, I will remain at a particular distance. So if I start closer to the equilibrium, I will not diverge from it or go away from it. So that is the idea of Lyapunov stability. So I can start really, really close to the equilibrium, and I can ensure that if I can ensure that the system will not, the trajectory will not diverge away from the equilibrium, then we say that the system is Lyapunov stable. And the second property is attractivity, and that is where asymptotic stability comes into play. And we say that if the trajectory not only is Lyapunov stable, but eventually it just goes to the equilibrium at an asymptotic rate, we say it is the equilibrium is attractive as well. Of course, this is a very primitive notion. There have been many variations of it, and one of the variations is where I use equilibrium, instead of using an equilibrium x star, I use a set of equilibria. So I can define properties of that equilibria and study the stability with respect to a set of equilibria rather than an equilibrium point. Another variation is where I use a different kind of norm, and then I get different kind of stabilities. And attractivity again can be, it does not necessarily have to be asymptotic. It can be exponential. And especially for max plus linear systems, we do see exponential convergence because of this turnpike phenomenon in max plus linear systems. Okay, so this brings me to the discussion on norms that are at our disposal. And in the end, we would like to calculate the ultimate bounds on the state. So let's say there exists some bound that eventually I will always be, wherever I start, I will always be this much close to the equilibrium state. So as for the norms, the first one is the L infinity norm. So that is your regular supremum norm. And the unit ball in, let's say for R2 is a square, and you can get like a hypercube for higher dimensions. So the next important norm is that of the Hilbert's projective norm, and this is quite important feature that I use. Again, this might not be a norm in the in the regular space, let's say R3, but under certain conditions, it can act as a norm on the projective space. So I project R3 onto R2, let's say by considering x3 equals 0, and I can then draw the level sets, and yeah, use it as a norm. So the difference between these two is that The first one considers distance from zero. So if I say that a norm is L infinity norm is being minimized, I would be reducing the volume of this square and shrinking it towards zero. For the Hilbert's projective norm, it is actually distance between the rays. So because it works on the projection, we are not actually looking at shrink towards zero, but we are looking at distances between rays. So it is a sort of contraction property as opposed to between rays as opposed to between points in R2 for in Rn for the L infinity norm. Okay, so for our case, we have a general dynamics, and again, we discussed the notion of stability. We would like boundedness at each event step k. So we would like that the norm of the state x of k remains, the Hilbert's projective norm remains bounded, and that is essentially for each step k, let's say 10, it is calculating this difference between these dashed lines. So it is giving me a bound on the state at particular event step k. So that is why I really like this particular norm, and especially for an application from an application perspective, it gives us a sort of it gives us exactly the make span of the system. So consider that we operate a production network, a manufacturing network once, and the states give us, so let's say it's linear. The first state gives us the time of completion of the first activity. The last state gives us the time of completion of the last activity for a particular event cycle. The difference between the time of the last one and the first one gives us how much time it takes for the raw material to come in and the product to get out. So that gives us the make span of the system, so that there is a physical aspect involved as well. Okay, so again, like I suggested, Lyapunov stability, I can use its variations. The first one is replacing the equilibrium point with an invariant set. So now I say that if my state lies in an invariant set in a set K, and my next state x of k, excuse me, also it remains in K, then this set K is actually positively invariant. And that is what I use in place of an equilibrium point. So for instance, for a max plus linear system, this could be the max plus eigenspace of the system, right? So that max plus eigenspace of a max plus linear system is invariant. So if I start on a max plus eigenvector, then I will remain at that particular max plus eigenvector. The next thing is attractivity. So the second part is, okay, we now consider distances in terms of max plus this Hilbert's projective norm, and we would like that asymptotically the distance of this x of k and the invariant set goes to zero. Again, this is I've written it in an asymptotic sense, but this could actually be achieved in finite number of steps. And then we have exponential convergence, right? So finally, if we are able to find this invariant set that is smallest in a certain sense and non-empty, then we can find an ultimate bound on the state. So if we find a set K that is invariant and attractive, and it is the smallest such set that exists. So we know that the state will eventually enter this set K, and we can find a bound such that for all states X in this set K, we have a bound, and this represents an ultimate bound, and this represents the ultimate make span of the system, right? So eventually I let the system run for enough time, then I will have like a bound on the make span of the system. So for us, I mean, these are very general notions, and we can look at the application of the tools I derived on the boundedness, to study the boundedness of a set of max plus matrices, right? So I study an open loop SMPL system, open loop switching max plus linear system, that is defined on a set of matrices A, this curly A, max plus matrices, and it's again the next step from max plus linear systems. So given an open loop SMPL system, given a set of matrices A, can we find a bounded common invariant set? So that is one of the questions. The other one can be, is this set that I find attractive? So first of all, is it the smallest? So can I construct it? And the third one, is it attractive? So if I am able to find an invariant set, can I say that I can start from some point and eventually all my trajectories will enter this set? So is it attractive? So these are the questions I try to answer for a set of, so a semi-group of max plus matrices. Okay, so I can make my life easier. So because I consider a simpler system, and this is where max plus theory helps me a lot. So I consider some certain well-behaved sets that can be represented as max plus cones, and even we can make them more well-behaved by looking at the max plus eigencones of some function, well-behaved function G, right? So I can look at simpler cases where G is a max plus linear function. So this is just A O times X, and eventually I will get a set that is very well behaved, especially if that matrix A is irreducible. So this is what I study in one of my conference papers. The first case is that, okay, if I have, let's say, two matrices, A1 and A2, and I derive somehow a third matrix, and I say that this set generated as a max plus eigencone of this matrix Q, can I prove that this set is, so I mean, if I can prove that this set generated by Q is invariant, so each matrix, when applied to a point and generated in this set, it stays in that set, then I have invariance property, and these sets, for the case of a max plus linear, so a max plus matrix is just a clean star. There are closed form solutions for generating such sets. So that is a very nice property. Very nice. That, yes.
I have a question. So in this S alpha beta, what are alpha and beta in this example?
Yeah, so in the paper, I keep it rather open. So what I say is that we can choose these beta and alpha at a certain cost. Of course, we would like that this set is fine, is non-empty, right? So we would like that beta is greater than alpha. If we go to the definition itself here, we would like that beta is greater than alpha, but we would also like to have that this set is non-empty, right? So, and we can change beta and alpha, and that has consequence, as I understand, on the growth rate of the system, right? So I can, if I decrease beta and alpha, keeping the set non-empty, I restrict the growth rate of the system. So I restrict, let's say, how much the system, the throughput of the system, in a sense. Am I making any sense?
Yeah, well, I just wanted to know what are the numerical values of alpha and beta in that example, because they are not given.
For that particular example.
You're just saying that they exist. For some alpha and beta, we have this. I'm satisfied with this answer.
Yeah. So for instance, here you would have a matrix Q, right? And then this beta would just be, I could take beta as the max plus eigenvalue of that matrix Q, especially because it will be an irreducible matrix. And alpha, I think there is a paper from Butkovich on the possible values of alpha such that this set, this set remains non-empty. And we can select it such that, so for instance, if we want that the states are growing, so if the states represent time, they cannot be, let's say, non-decreasing, right? So xk minus 1 will always be greater than 0, greater than equal to 0. So then alpha can be simply taken as 0. So in that sense, we can select it.
Okay, that's fine.
Okay. So we can select, we can choose more complicated functions G. One of them is using, let's say, a topical function, a minimum, pointwise minimum of maximum a pointwise minimum of a maximum of some matrices, let's say max plus matrices. And again, we can generate in that particular example, I generated as two different, so the eigencone being generated by two different matrices. And the idea is that I can restrict how I switch between these two systems. So if I say that, okay, yeah, I mean, arbitrary is too conservative for me. Let's say I can only switch in a certain way between these two matrices. And if I can bring in that information, I can find better bounds on the ultimate make span of the system. So this is more or less what I do here. So again, there are a lot of tools that can be extended using the that we can derive using the tools that I present in my thesis. Okay, so like I suggested, if it's a simple max plus matrix, then it is generated using clean star. The sub-eigencone, we can generate it as a closed form expression under some restrictions, of course. And I really like, I mean, I just gave it a name. So it's, so first of all, I say that generalizing the properties of a clean max plus column span of a clean star matrix, I can say that it is finitely generated. It is actually also a convex set in the conventional sense, and it has a compact projectivization. So there are some papers on it and that relate these properties to that of the column span of a clean star matrix. And I study because I talk about this this particular bound on the state X. So what I can say is that this particular inequality, that X, the Hilbert projective norm of state X is more than equal to delta, can be actually represented as a as the max column span of a special clean star matrix. So that is the idea. I choose clean star matrix. I work with it. Okay, so what I derive is a constructive theorem. So I say that, okay, if a set K, if it exists and it is derived as the column max plus column span of a clean star matrix, then I can rewrite the condition of invariance using a simple equality. And this is fairly easy to check if I already have this matrix K. But if I do not have this matrix K, I can actually parameterize and solve for those parameters, because this is in the end just like an equation. I can minimize, let's say, some feature of this matrix K, and so that particular inequality, I mean, it is satisfied as an equality in the end. And I can, so these are actually just mixed integer. So these, I can write this inequality, this program as a mixed integer linear program. So it will be a linear program with certain, actually certain variables, auxiliary variables that will be binary, not even integer, all integers. So I can, how I say, calculate the volume of this matrix K is using what I call the second largest max plus eigenvalue. I don't think Sergey likes that terminology, but the idea is that that a Klein star matrix has zeros on the diagonal, and we know that the largest max plus eigenvalue of a Klein star matrix here is 0 because of this max plus identity matrix. And what I do is I replace all the diagonal elements with an epsilon. So I take away the largest max plus eigenvalue, and the one that is remaining I call, so the one that I calculate by in that way is I call lambda 2. So this, you see, one E is just an equation for deriving the max plus eigenvalue. I just don't do it for calculate it for I equals j. So I minimize it. So minimize minus lambda 2 actually, and I try to find the smallest possible set, and I can solve it as a mixed integer program. So I can do more things. I can talk about scaling of this matrix. Again, there are certain ways I can scale this particular set generated as the max plus column span of K. And I say that if I am in K0 here, and I map into K minus 1, at the next step, then I'm contracting, and I'm, let's say, if I can prove that I can do it certain number of times, then I arrive at the smallest set that is, let's say, attractive, right? So if everything in K0 is mapped to K minus 1, and then everything in K minus 1 is mapped to K minus 2, and I already know that K minus 2 is invariant, and I cannot, so let's say the next one, next contraction does not happen, then I can say that this set K minus 2 is attractive. So I can write that again as a mixed integer, so a parametric mixed integer program, right? So I can say that I try, if my xk minus 1 is in this K delta, and the K mu is contained in K delta, and I say that it contracts and the next state is actually inside. So I can calculate the rate of convergence as a parametric mixed integer program. So again, this is a sufficient condition. The actual program looks a bit more complicated. This is easier on the eyes. And the idea is that if I can prove that this program is feasible, then I can prove that the system trajectories will be attracted to the set K. That is the idea. Okay, so yeah, again, I show it for different, let's say, a bimodal switching matrix linear system that starting from some infinite steps, I can reach set K. That is what this graph suggests. So I can prove the existence. So let's say I gave like this nice, I say that this is constructive. I can write it as a mixed integer program to find K, but I can also write this particular equation as a two-sided max plus linear equation. And there are algorithms to show that if a finite solution exists, then it is actually, we can prove the existence of this particular common invariant set. Again, this is just an existence, right? So this is not an optimality. There is no optimality involved. So there can be, it might not be the smallest one, let's say. Okay, so yeah, in conclusion, I studied tools from conventional physical systems. To study conventional physical systems, I imported that knowledge of those tools and stability notions to man-made systems that I did derive using max plus algebra. And yeah, I studied I derived those tools, and I studied those. I used those tools to study the boundedness of matrix semigroups in max plus algebra, and to find suitable invariant sets and their properties. And yeah, I can formulate a lot of problems as mixed integer linear programs. So in future, I mean, some of the things I've already done and not presented here, we can extend it to the case where switching is constrained, like I suggested. Arbitrary switching might be too conservative for application. We can extend it to the case where we actually have inputs to the system, let's say delays, and we can also study the relationship of the suggested algorithms to topical optimization. And from algorithmic perspective, we can also study not a single cone but multi-cones. Again, these are I mean, these steps have already been taken for conventional time-driven systems, and we can follow that framework and derive a lot of tools to, as long as it makes sense for discrete event systems. That's it from my side. Thank you very much. I'm open to questions now.